In this presentation, I'm going to talk about trace element composition of clinopyroxenes from the Kızıldağ ophiolite. Ophiolites are important rock assemblage which submits most of the information about the evolution of oceanic lithosphere. Mantle peridotites representing the bottom section of the sequence is also important to provide information about the oceanic lithosphere formation, melt extraction at mid-ocean rich environment, and melt-mantle interactions during diapric rise of melts through upper mantle. The focus of this study is on the generation of melts forming peridotites and their compositions to explain mid-ocean rich basalt petrogenesis. Clinopyroxene rare earth element compositions from cumulates are used to draw conclusion for the composition of melts interacted into the oceanic crust. We report measure trace element and mineral chemistry contents of minerals, mostly clinopyroxenes, from the peridotites of the Kızıldağ ophiolite. Kızıldağ ophiolite is composed of the mantle and crustal rocks exhumed during the closure of the Tethyan oceanic crust. The main body of the ophiolite extends 30 kilometers in a northeast-southwest direction along the eastern coast of the Mediterranean Sea, consists of a serpentinized hasburgite and mantle peridotite core overlain by gabbros, sheeted dikes, and extrusive rocks. Here we can see the study field and some hand samples. The serpentinization can be seen here commonly, and the pyroxenate veins cutting through hasburgite body. Here are the BSE images of hasburgites. Usually recrystallized clinopyroxene grains observed between orthopyroxenes and olivines. Porphyroclastic texture was observed in depleted hasburgites. Mantle hasburgites show porphyroclastic textures. These hasburgites include kinked orthopyroxene porphyroclasts. Some samples show symplectic texture with spinel and clinopyroxene association. Serpentinization is dominant and commonly obscures the primary igneous mineralogy. Hasburgites represent the oceanic peridotite composition with their model mineralogy. Peridotites of Kızıldağ ophiolite composed of hasburgites, lerzolites, whellites, and danites. If we check the whole rock major oxide contents of the peridotites, silicium oxide, titanium oxide, aluminum oxide, manganese oxide, and calcium oxide show coherent variations with respect to magnesium oxide, whereas sodium oxide show horizontal lineation. Impregnated hasburgites are enriched in aluminum oxide, calcium oxide, titanium oxide, and sodium oxide, relative to tectonized mantle hasburgites. Peridotites from Kızıldağ ophiolite show slight spoon-shaped rare earth element patterns with small twists in La, Ce, and Pr. Large iron lithophile elements such as cesium, strontium show positive anomalies. Nickel and cobalt are known as compatible during partial melting. They show clear positive correlation with increasing magnesium oxide content. Nickel contents of hasburgites are higher than the impregnated hasburgite samples. Ytterbium is highly compatible with garnet and incompatible with clinopyroxene and spinel. Some impregnated hasburgites have higher ytterbium compositions. In addition, they are residues after 15% partial melting, which indicates that they were depleted in garnet field first. All rock major oxide compositions of upper units given here for comparison. All Hasbugites have high magnesium oxide contents and low aluminium and calcium contents. Impregnated and mantle Hasbugites show end-to-end patterns reflecting homogeneous patterns, and they have similar compositions with oceanic and ophiolitic peridotites. Impregnated ones show wide compositional variations. Cumulate rocks of the upper part of the sequence reflecting higher calcium oxide, aluminum oxide, and silicium oxide, and lower iron contents than mantle Hasbugites because their composition based on the clinopyroxene chemistry. Spinels in peridotites are primary and they have magnesium numbers between 37.1 to 67.3 and show no diversity between impregnated and depleted Hasbugites. Titanium oxide contents of spinel in the impregnated Hasbugites and ultramafic cumulates vary considerably, but residual Hasbugites have the lowest titanium oxide contents. Chromium number of spinel in impregnated and depleted mantle Hasbugites show similar compositional range between 46.8 to 62.3 and 49.3 to 70.4. Spinel chromium number and magnesium values compared with partial melting degree for comparison. Most of the spinel compositions lies within the oceanic peridotite field. Both the impregnated and depleted Hasbugites show similar chromium number variations. They also have similar compositions with peridotites from East Pacific rise, except for the most refractory Hasbugites. These high magnesium number spinels of Hasbugites are located in the field of Western Pacific margin. Here we can see them. Titanium oxide contents of spinels from impregnated peridotites are clearly distinguished from the depleted Hasbugites. Impregnated samples show higher titanium oxide compositions than depleted Hasbugites. Here, the peridotites with high titanium. Check the mineral chemistry of the peridotites. Olivine is the most abundant phase among studied peridotites. Forsterite content of the olivines from impregnated Hasbugite has a narrower range compared to the mantle Hasbugites. Hasbugites of Kızıldağ phyla show similar variations with Oman Hasbugites. Here we can see the similarities with South Oman Hasbugites. Olivines in depleted Hasbugites have similar chemical characteristics with residual olivine in primary Hasbugites. Nickel oxide contents of olivines from Hasbugites between 0.30 to 0.51 weight%, and they follow the olivine mantle array range. The range is here. Clinopyroxene in Hasbugites and impregnated Hasbugites have chemical heterogeneity, and they show a wide range of magnesium numbers. Clinopyroxene in impregnated Hasbugites show enriched compositions than depleted mantle Hasbugites. Titanium oxide contents of the clinopyroxenes from peridotites of Kızıldağ ophiolite shows similar variations, and depleted Hasbugites has lower clinopyroxene titanium oxide content than those in impregnated Hasbugites. Orthopyroxene is the second most abundant mineral phase in mantle rocks of Kızıldağ ophiolite. All orthopyroxenes are in enstatite composition. Mantle Hasbugites and impregnated Hasbugites have enstatite between 84.8 to 89.5 and 83.4 to 89.8 respectively. Orthopyroxenes in peridotites have compositional variations of aluminum oxide from 1.07 to 2.56 weight% and calcium oxide from 0.63 to 4.13 weight%. Mantle Hasbugites have depleted patterns from middle rare earth element to lighter rare earth elements. Impregnated clinopyroxenes show more enriched middle rare earth element and light rare earth element patterns, which are similar to abyssal peridotite clinopyroxenes from normal rich settings. Clinopyroxenes show have rare earth element enrichments between 1 to 10 times compared to chondrite values. One sample is more depleted than the depleted CPX values of the Habsburgite ophiolite, Ullmann Habsburgites. Impregnated Habsburgites have different CPX rare patterns, rare earth element patterns than those of mantle Habsburgites from the lower part of the sequence. Clinopyroxenes, interstitial to orthopyroxene, and olivine in impregnated samples have slight convex upward patterns. Dysprosium 2 ER enrichments can be seen here. Clinopyroxenes from all Habsburgites show slightly enriched light rare earth patterns. We can see the light rare earth enrichments here. Heavy rare earth element abundances in the clinopyroxene from the impregnated Habsburgite samples are significantly greater than those in mantle Habsburgites. All clinopyroxenes are enriched in hydrophile elements and depleted in high field strength elements. Trace element compositions of orthopyroxenes are similar to clinopyroxenes. They have rare earth element patterns depleted in light rare earths. Orthopyroxenes in all Habsburgites are depleted in mid rare earth elements and show no enrichment in light rare earths. Impregnated Habsburgites have similar compositions to the Ullmann periodicites, and 2 Habsburgite samples show fertile orthopyroxene heavy rare earth element composition similar to the larzolites of Ullmann ophiolite. Mid rare earth to light rare earth compositions of Habsburgite generally low. Primitive mantle normalized multi-element composition of orthopyroxenes show positive anomalies of fluid mobile elements. Here we can see PB and Li. And low concentrations of RB and TI. They are below detection limits. Here we try to explain the origin of the periodicites from Kızıldağ ophiolite by using pyroxene rare earth element chemistry. We applied clinopyroxene rare earth model calculations to simulate the multi-stage melting in Kızıldağ Habsburgites. The Habsburgites of Kızıldağ ophiolite show more depleted clinopyroxene rare earth element patterns than primitive mantle compositions. According to the mantle model, such depletion can be materialized by fractional melting in the garnet or spinel field meltings around 10 to 20%. Consequently, two-stage partial melting history and melt-periodotite interaction has the main effects on the formation of Kızıldağ periodocites. Mantle Habsburgites of the Kızıldağ ophiolite have clinopyroxenes with high light rare earth depletion. Such rare earth patterns for residual Habsburgites can be formed by fractional melting of a mid-ocean rich basalt metal in the stability field of spinel. The most depleted clinopyroxene rare earth patterns of residual Habsburgites are not compatible with this approach. It has been reported in previous studies that extremely depleted rare earth patterns of clinopyroxenes can be related to a hotspot magma process. The ultra-depleted rare earth patterns observed in Kızıldağ ophiolite cannot be explained by simple spinel field process, but they can be explained by two-stage garnet plus spinel field melting. Simple spinel field melting seems insufficient for light rare earth depletion in clinopyroxenes. Multi-stage fractional melting is required to deplete light rare earths of clinopyroxenes from residual Habsburgites. Such light rare earth depletion was observed in clinopyroxenes from mantle Habsburgites of the Otris ophiolite, and it is explained by 12% to 20% spinel field fractional melting, and additionally 4% melting in the garnet stability field. Spinel chromium number is known as a good estimator for the degree of partial melting. The range of total melting estimated from Kızıldağ periodotite is about 15 to 25%. This is clearly compatible with the clinopyroxene rare earth estimations. Most of the olivine and spinel compositions, Habsburgite from Kızıldağ ophiolite, plots on the edge of the residual mantle array. Spinel chromium number of mantle peridotites has a wide variation, which indicates variable degrees of partial melting. Depleted mantle Habsburgites of the Kızıldağ ophiolite represent an arc setting which is consistent with polygenetic origin of Tethyan ophiolites and suprasubduction influence with young bonanites. We can here see the bonanitic interaction, melt rock interaction signs. CPX ytterbium and dysprosium concentrations of mantle peridotites significantly separate mantle Habsburgites and impregnated Habsburgites from each other. Impregnated Habsburgites show similar compositions with abyssal peridotites. Depleted mantle Habsburgites of the Kızıldağ ophiolite represent an arc setting which is consistent with the polygenetic origin of Tethyan ophiolites and suprasubduction zone influence with young bonanites. The depletion of clinopyroxene rare earth elements in mantle peridotites of Kızıldağ ophiolite were compared with the calculated melting curves. Except one Habsburgite sample, all Habsburgites show compatible depletion trend with 10% garnet stability field. With the opening of oceanic lithosphere, garnet lazuli underwent partial melting up to 10%. Upwelling asthenosphere lifts the partially melted rocks through the spinel stability field, and melting keeps proceeding in the shallower depths, around 20 to 40 kilometers. 5 to 10% spinel field melting is calculated for the mantle Habsburgites, with a total 20 to 25% melting in garnet and spinel fields. Both and these results are compatible with mineral chemistry results. Mantle convection induces to the formation of light lithospheric mantle by moving horizontally. Significant characteristic of clinopyroxene rare earth pattern is the enrichment in light rare earths and large ion lithophiles for the mantle peridotites. This indicates interaction with subduction metasomatism. Some higher field strengths and heavy rare earth elements such as SC and ytterbium respectively, as known as highly incompatible with clinopyroxene and spinel, but compatible with garnet. Primitive mantle normalized multi-element variations peridotites show positive SC anomalies and high ytterbium compositions. If these rocks are products of spinel stability field, Habsburgites has to be depleted in SC and YB. SC anomalies indicates that melting occurred mainly in the garnet stability field. Depleted Habsburgites with high ytterbium concentrations indicating a complex melting history for the formation of these peridotites. Higher melting degree estimations and high spinel chromium number values, in addition, depleted whole rock compositions are reflect garnet and spinel feed meltings consecutively. Mantle metasomatism is also effective on the chemistry of the Habsburgites. All clinopyroxenes from mantle peridotites samples show light rare earth and large ion lithophile enrichments, also titanium enrichments of spinels, indicating mantle melt interaction. This result is also accordance with petrographic contents of impregnated Habsburgites, which includes secondary clinopyroxene crystals. Tectonic setting of Kızıldağ ophiolite leads us to a multi-stage partial melting history, as mentioned above. First stage melting thought to have started in a mid-ocean rich environment, and subsequently the spreading movement switches to a closure movement, which turns into a suprasubduction zone setting. Impregnated Hasbogites and mantle Hasbogites, which represents first mantle residual rocks, underwent 10% partial melting in the garnet stability field. While ocean floor spreading continues to form mid-ocean ridges, upwelling mantle lifts these residues to the spinal stability field and partial melting keeps proceeding. As subduction takes place, previously melted samples undergone 10 to 12% spinal field melting, with a total 20 to 22% melting, and all Hasbogites represent metasomatized characteristics due to the melt rock interaction with mid-ocean ridge and suprasubduction zone settings.